In this video, we're going to go over how derivatives affect the shape of a graph. So what does f prime say about f? So to see how the derivative of f can tell us where a function is increasing or decreasing, we can just look at the graph below, right? So if the derivative, which is the slope, is positive, the original graph is increasing. So we can see from a to b, the slope is always positive, so we have a positive slope. So our graph is increasing. From B to C, our graph is decreasing, and that's where our slope is negative, so negative slope. And then again, from C to D, the graph is increasing, and that's where, again, the slope is positive. It's a positive slope. So there's a thing called the increasing decreasing test. And basically what this is that if the derivative is greater than 0, so if the derivative is positive, meaning that the slope is positive, then f, the original function, is increasing on that interval. If the derivative is less than 0, meaning that the derivative is negative, then the original function f is decreasing on that interval. So we're going to look at this example here, and we have to find where the function is increasing and where it's decreasing. So what we're going to do is find the derivative, and then we're going to see where the derivative is equal to 0, which is going to be where I have a slope of 0, and then we're going to kind of use that to figure out the points around that, whether or not the derivative is positive or negative. So first thing we'll do is find the derivative. So f prime of x, we're going to get 12x cubed minus 12x squared minus 24x. So we're going to set this equal to 0. So we're going to factor this a little bit more. I'm going to pull out my GCF, so I'm going to pull out that 12x. So I have x squared minus x minus 2. Set it to 0. Again, I'm going to factor a little bit more, so I have the 12x on the outside. This will become x plus 1 and x minus 2. Set it to 0. So when I set 12x equal to 0, I'm going to get x equals 0. When I set x plus 1 equal to 0, I'm going to get x equals negative 1. And when I set x minus 2 equal to 0, I'm going to get x is equal to 2. So those are all of my points on my original graph where I have a horizontal slope. So now what I'm going to do is make a little chart here. So I'm going to make an f prime chart. Okay, so there's different ways to do this. If you find a better way that you like, you can make your chart however makes sense for you. So basically what I'm going to do here is the three values that I have for when my derivative is 0, what I'm going to do is put in order. So I'm going to put negative 1 here, I'm going to put 0 here, and I'm going to put 2 here. So what I'm trying to do is pick values that are like to the left of negative 1, so less than negative 1, between negative 1 and 0, between 0 and 2, and greater than 2. So I'm going to, let's say, pick a value that's less than negative 1, right? So let's say like negative 2. So you can actually plug these numbers in if you want to, or just kind of think about it in terms of like a larger negative number. So I'm going to plug it into my derivative. You could plug it into any step of the derivative, so you can plug it into the original, or you can plug it in any of these simplified. I usually like to plug it into this one here, whatever's like most factored. It's a little bit easier to work with. So if I plug in a number that's less than negative 1, so like negative 2, if I multiply it to 12, this is going to give me a negative number. A negative, let's say 2 plus 1 is going to give me a negative number. And then a negative 2 minus 2 is also going to give me a negative number. So when I'm plugging this in, I have a negative times a negative times a negative, which is going to give me overall a negative. So I don't really care about the actual value of the number. I just care about the sign of that number. So when the derivative is negative, if I look at my little increasing decreasing test chart up here, when my derivative is less than 0, then f is decreasing. So I'm just going to put a little arrow and say that f is decreasing. So in the interval from negative infinity up to negative 1, I'm decreasing. Okay, so then between negative 1 and 0, so I'm going to pick like negative a half, right? So negative a half is going to give me a negative number here. Negative a half is going to give me a positive number here. Negative a half is going to give me a negative number. So I have a negative, positive, and negative. When I multiply them all together, that's going to give me a positive. Okay, so then if my derivative is positive, that means that my original graph is increasing. I'm going to pick a value between 0 and 2. So like whatever, 1. And you don't want to include 0. So you don't want to pick 0 and you want to pick 2 because that's going to give us 0, which we don't want. So I'm going to pick 1. I'm going to plug it in. This is going to give me a positive. This is going to give me a positive. This is going to give me a negative. So positive times negative is going to give me a negative. So then again, here it is going to be decreasing. And then I have to pick a number greater than 2. So whatever, 3 or 4 or whatever, plug in a number greater than 2. So that's positive, positive, and positive. So this is going to give me a positive. And that's going to be increasing. So where we have, oops, I just clicked that. Where we have our increasing intervals, it's going to be increasing from -1 to 0. Oops. -1 to 0. And from 2 to infinity. 2 to infinity. And notice I'm not using brackets. I'm not including those values because at -1 and at 2 and at 0 is where the derivative is equal to 0. So it's not going to be increasing there. It's going to be horizontal and not moving. And then it's decreasing where my slope was negative. So from -infinity to -1. And then again from 0 to 2. So these are my increasing and decreasing intervals. Okay, and the graph of f, so here's the actual graph of f, it confirms the information in the chart. So we can see that based off of here, it's increasing from -1 to 0. So here's -1 to 0, it's increasing. It is also increasing, we could see from 2 to infinity, which matches this, 2 to infinity. It's decreasing, -infinity to -1, -infinity to -1, and then again from 0 to 2. So looking at the graphs of f and f prime, so f is our red graph and f prime is our blue. So this looks like a little bit weird, I guess, but the f graph is the graph from the previous slide. So looking at this, right, it's the same graph. Blue is our derivative graph, and we can see that how they compare over a certain interval. So on this interval that's like colored in pink or red or whatever, the original graph is decreasing, and the derivative graph is below the x-axis. It's negative. Okay, same thing in this green piece. We have the red is increasing, and the blue is above the x-axis. And then in this piece, the red is decreasing, the blue is below the x-axis. And then in this green piece, the red, the original, is increasing, and the blue is above the x-axis, so it's greater than 0. So again, here's the same exact function that we used before. Now looking at this, we want to see where we have local max and mins. Okay, so looking at this, I can see that here is a minimum, right? I can see that, I'll change colors. Here is a maximum. I can see that here is a minimum. Okay, so just looking at the graph, I can see that this is an absolute absolute minimum because it's the lowest point on my graph. What we did last class with making those charts and finding the critical points and plugging them in and doing the end points and trying to find where's the largest and smallest numbers. So that's how we find the absolute. But we haven't talked about how we find the local max and local min. So there's still going to be critical points that are going to be helpful to us. So looking at this, we can see that the blue dot that I put here, that is f of -1, and that is going to be a local min. We can also see that the red dot that I made there, that's f of 0, and that is a local maximum. And then the green dot, that's f of 2, and that is also a local minimum. So even though that is also the absolute minimum, we're focusing right now on the local maximums. Okay, so there is a specific type of test that we use called the first derivative test. So they're saying that suppose that c is a critical number of a continuous function f. So remember, critical numbers are those values that we get when we take the derivative and we set it equal to 0 and see where it also does not exist. Okay, so it's where the derivative is 0 or does not exist. So if f prime changes from positive to negative at c, then f has a local maximum at c. So just think about it. If f changes from if f prime, if the slope is changing from positive to negative, so here's a slope positive, and then it changes to negative slope, here you have a maximum, right? So that's a local maximum. If f prime changes from negative to positive, so slope of negative, and then it changes to positive, okay, here you're going to have a local minimum. Okay, and if it doesn't change at all, then it's neither a local max nor a local min. Okay, so here's a couple of examples. So we have a local max here because the slope is positive and then it changes to negative. Here the slope is negative and it changes to positive, so we have a local minimum. And these two bottom examples, they don't have a max or min because they are constantly either increasing or decreasing. So here we can see the derivative is positive, then the derivative is 0, and then the derivative is positive. So it's not changing signs. Same thing here, we have a negative slope, we have a 0 slope, and then we have a negative slope again. Okay, so we're going to utilize this first derivative test. So find the local maximum and minimum values of this function here. Okay, so the first thing we want to do is we need to figure out our critical values. So we're going to take the derivative of this and then set it to 0. So we have 3x squared minus 27. Okay, so I'm going to set this equal to 0. Since this is a polynomial, I'm not going to have any place where the derivative does not exist, so I don't have to worry about that. So we're going to factor out the 3. So we have x squared minus 9, set it to 0. And then I can factor x squared minus 9 more, so x plus 3, and x minus 3. So when I set this equal to 0, the 3, that's the constant, can just be divided out. So I end up just getting x equals negative 3 and x equals positive 3. Okay, those are my two critical points. So now what I'm going to do is I'm going to make the same chart that I made before when I did increasing and decreasing. So I'm going to make an f prime, little chart here, and I'm going to put the two critical points. So negative 3, make sure you put them in order, and 3. So what we're going to do here, again, is pick a value that's less than negative 3 for this first box. And again, I will plug it into this. Okay, I can ignore that 3 because it's just a constant. So I'm really just plugging it into this x plus 3, x minus 3. So if I pick a number that's less than negative 3, so negative 4, this is going to give me a negative value. This is going to give me a negative value. So negative times negative is going to give me positive. So that means that the original graph is going to be increasing. I'm going to pick a number between negative 3 and 3. So I'm going to pick whatever, 0. So if I pick 0, this is going to give me positive. This is going to give me negative. I multiply them, I get negative. So my original graph is decreasing. And then pick a number greater than 3. So if I pick 4, this is going to give me a positive. This is going to give me a positive. When I multiply positive times positive, I get positive. And that means that my original graph is going to be increasing there. So I'm looking to see where it changes signs. So at negative 3, it changed from increasing to decreasing. So my original graph is going to look like this. So that means that I have a local max, and the x value is going to be negative 3. So negative 3. If I want to find the y value, so from trying to graph this and I want to find the y value exactly, what I'm going to do is take this negative 3 and plug it into the original function. So negative 3 goes into the original function, and if we do that, we get 34. Okay, and then I can see here that it's changing from negative to positive, so it's going from decreasing to increasing, so like that. So at 3, I'm going to have a local minimum. So again, the x value would be 3. If I wanted to find the y value, I would plug it into the original function, so this one, and I plug in 3 for x. And then in this case, I would get negative 74. So there's my local max and local min. Okay, so again, another example, find the local max and min. So first step, as always, is find the derivative. So g prime of x, if I take the derivative of x, I get 1. The derivative of 2 sine x is going to be 2 cosine x. Okay, so I'm going to set this to 0. So I'm going to move this over actually. So 1 equals negative 2 cosine x. So I'm going to divide by negative 2. So cosine x is equal to negative 1/2. So I want to figure out the cosine of what is negative 1/2, and I'm in the interval between 0 and 2 pi. So that would be when x is equal to 2 pi over 3 and 4 pi over 3. So that's when the cosine will be negative 1/2. So again, I'm going to make a chart here. So f and f prime. But in this case, because we have an interval between 0 and 2 pi, we can't go like to negative infinity and positive infinity. So I'm going to put the 0 here. That's my endpoint. My first critical point, I have 2 pi over 3. My second critical point, I have 4 pi over 3. And then, actually, I'm just going to erase this last piece at the end, right? Because it's not going to infinity, so you don't have any piece like to the right. And then this is my right endpoint, so that's 2 pi. Okay, so again, you're going to pick a value between 0 and 2 pi, and you're going to plug it into the derivative. So if we do that, this is going to be positive, which means the original graph is increasing. Okay, then we have negative, which means the original graph is decreasing, and then we have positive here, which is increasing. Okay, and we also just want to be careful, so don't assume that every time you have the values written here that it's going to change sign every time, because that is not the case. So sometimes you're going to have the same sign next to each other, so we can't just assume that it's always going to be alternating signs. So now I look to see, okay, well, here it's changing from positive to negative, so that's going to be a local maximum, and then it goes from negative to positive, so it's decreasing to increasing. So here I have a local minimum. So I have a local max, and that happens at 2 pi over 3. And if I plug that in again to the original function, that's going to give me 2 pi over 3 plus root 3 as my y value. And then for the local minimum, we've got 4 pi over 3. And then the y value would be 4 pi, over 3 minus root 3. And that's from plugging it into the original function. Okay, and here's a graph of the original function, and we can see that the local maximum occurs here. We can see that the local minimum occurs here. Okay, let's look at this last example. So the graph of the derivative f prime of a function f is shown. On what intervals is f increasing or decreasing? And at what values of x does f have a local max or a local min? So here we don't have to find anything because we don't have the function. We're not actually given it. But if f is increasing, that means that, well, so we're looking at the graph of the derivative. So we always want to make sure we're paying attention to what graph we're looking at. So if f is increasing, that means that it has to be above the x-axis. And if f is decreasing, that means it has to be below the x-axis, the derivative graph. So we can look at our graph and we can see that it's above the x-axis. I'll try to highlight. Oh, highlighter. Yeah, let's do that. So it's above the x-axis here from 0 to 1. It's also above the x-axis here. So we've got, I'm just going to put A here. So it's increasing from 0 to 1 and 5 to 7. And then we can see that it is decreasing here, because this is all below the x-axis, and then here's also below the x-axis. So we are decreasing from 1 to 5, and then again from 7 to 8. For part B, at what values of x does f have a local max or min? So where we're looking on the derivative graph for local max and mins of the original function, you want to be careful. So you're not looking at the bumps here and saying, oh, here's a min, here's a max. Because the mins and maxes are critical points, that is where the derivative is equal to 0. So it's going to be where the derivative graph crosses the x-axis. So we're crossing the x-axis here, here, and here. Okay, so these big dots, that's where we're crossing the x-axis. So in order to figure out where it is a local maximum, so I'm just going to draw this here. So I have a maximum if it goes from increasing to decreasing. So increasing means the derivative is above the x-axis. So when you're looking at the derivative graph, if it's going from above the x-axis to below the x-axis, that means that you're going to have a maximum. So I'll write that here. F prime goes from above to below. And then when I have decreasing to increasing, right, I have a local minimum, and that happens when it's decreasing. That means the derivative is below the x-axis, and when it's increasing, it's above. So that means that f prime is going to goes from below to above. So for part B here, I have a local max. And the local max happens at x equals, so wherever it's going from above to below. So it's going from above to below at 1. It's also going from above to below at 7. So x equals 1 and x equals 7. Because I can't figure out the y values of the original function, but I do know that the x values are going to be at 1 and at 7. Then I have a local min, and that's going to happen where f prime goes from below to above. So below the x-axis to above, that happens at x equals 5.